All right, ladies and gentlemen, let's talk a little bit today. This is Mark Anderson from Kellogg Community College, and we're looking at applications with variation, in particular direct variation and indirect variation. We're going to talk about these applications and how we can solve these equations with fractions in them. The direct variation problems and indirect variation problems look like two different kinds of equations. This is an example of a direct variation equation, where one thing directly affects another, and it has a picture that looks like a either positive or negative slope, with k being that slope of the problem. An indirect variation problem looks like this, where the k variable is underneath the x, and if you took a look at that on our screen, it would look like this. Now, for the story problems, we mostly focus on the first quadrant, but I wanted to show you all four quadrants because the indirect variation equation, if you plug in any scalar for k, which is a positive or negative whole number, or a decimal, this would affect how these graphs would look. Either the graph would go up or down based on positive or negative natures of k, and this would either look like this or like this, depending again on positive or negative values of k. Now, that's the academic side of things, but let's now get into the actual how to solve these problems kind of thing. Because what we're going to do first is we're going to have three different steps for direct and indirect variation equation problems. The first thing we're going to do is we're going to write the equation. The equation will then have the either, if it's direct, it's going to have y equals kx, and if it's indirect, it'll be y equals x over k. The second thing we're going to do is then we're going to solve for k and figure out what that scalar is, what that letter k is. Then number three is going to be write the new equation and use it in solving the sentence. So write the new equation, and the new equation will have k known in the problem, because we're going to start out with k unknown and figure it out. So let's show how this kind of plays out. And I only have 5 examples here, so these go pretty quickly. So it says if a distance d of a spring will stretch, and the distance will stretch, and how it stretches varies directly. So this is a direct variation equation. So as soon as I see direct or indirect, I'm going to write down my equation, whichever one is the right one to use, as the force F is being applied to the spring, which makes sense because you're going to see a spring is going to stretch as some force F, or with with the weight of the string being put onto it, it's going to stretch some distance d. So now you're actually given some information. So it says if a force of 12 pounds is required to stretch a spring 8 inches, so we know in this situation that we are putting 12 pounds of force onto the spring that stretches 8 inches, and so in this case the distance d varies directly as the force F. So you have to read the problem to figure out which letter, y or x, is your distance or force. And in this case, it sets it up pretty much as it's read. The distance is equal to the k times the force. Now, it tells you in the problem if a force of 12 is required to stretch a spring 8 inches, what force will be required to stretch the spring 12 inches. So this is going to figure out our letter k, and if I divide both sides by 12, k is equal to 8/12 or 3/4. Or you could change that into, 8/12 isn't 3/4, 8/12 is 2/3. Sorry about that. So what we're going to do is now take that 2/3 and plug it in for our k in the second part of this equation, because it says what force is required to stretch the spring 12 inches. So now we have our distance equals 2/3 times F, and now we're going to plug in our stretch of 12, and that would be into our distance. So distance is 2/3, distance equals 2/3 times F. And there are many ways to actually get rid of this 2/3. Since 2/3 is being multiplied by F, you can divide both sides by 2/3. And if you have the technology or graphing calculator, you can do that. Another way to do it is to multiply by the reciprocal. But again, as long as you get the right answer, you're going to pretty much do fine. If by multiplying by 3/2, we can cross multiplication, we can do some cancellation there, or 6/6 makes 1. So the F is equal to 3/2 times 12, or 1.5 times 12, which is 18. So you would need 18 pounds of force to drop that object 12 inches from its original position. So you'll hear me talk through these problems and identify right away whether it's direct or indirect, and then solve the problem, and then try to see where we're going to go here. Let's see, the stopping distance S of a car varies directly. Okay, so the stopping distance S varies directly, so it's going to be K of X, but as the square of its speed. Okay, so in this case we have to change the equation just a little bit, because it threw in this modifier that it's the square of the speed. Now granted, this still kind of fit the pattern of y equals kx, but in this case sometimes you're going to have a little modifier on the end of there, and we can still solve for it, just like we did before. Now here's where we set up and to find our k. If a car traveling 40 miles per hour requires 150 feet to stop, so we have the s, which is the stopping distance, so that's 150 feet, and then the speed is our 40, and we're going to square that. Find the stopping distance if the car is traveling 50 miles an hour. And this makes sense because the stopping distance isn't going to be, it's going to be a direct variation, but it's going to be multiplied, or there's going to be a power magnitude for how fast you're going. That's why traveling, just 10 miles an hour difference isn't going to just add another 10 miles or 10 feet to this stopping distance here. So we're going to solve for k, and 40 squared is going to be 1600. And we're going to divide both sides by 1600, and I strongly recommend decimals here because that would give us a 0.09 as my k factor for solving for the problem. So my stopping distance is equal to 0.09 times your speed, or velocity in this case, squared. So now we're going to, instead of plugging in 40, we're going to plug in 50 and check out our stopping distance. 0.09 and the 50 squared, and that 50 is going to get huge because it's being squared, but the 0.09 is there to modify it a little bit. So we're going to have 0.09 times 2500, and if we do that out, the stopping distance for just 10 extra miles per hour is going to jump from 150 to 225 feet. So you can see why adding just an extra 10 miles an hour greatly increases the stopping distance because the problem was squared. Alright, so now what we're going to have is our first problem dealing with inverse variation. Okay, so now here for this problem, our third of 5 problems, it says the speed of a gear varies inversely. Okay, so what we have is y equals, in this case x over k, as the number of teeth t. Alright, so the speed, v, varies inversely as the number of teeth t. And, I should have put a t there. Sorry about that. Okay, now to explain this problem a little bit, think about a bike that can change gears, 10-speed, your fat tire bike, your mountain bike, that might have some small gear changes to make. When you shift to a cog or a wheel that actually, or a gear setting that has fewer teeth, it is harder to push it. But the speed, every single crank you do at that harder push is going to make the wheel go faster because you have a lot of work to do on that back wheel with fewer teeth. But in a lower gear, where it's easier to push, then there's more teeth, so it's easier to push, but you go much slower. So now here we have a gear that has 30 teeth. This little line here represents the first half of the sentence that will help us solve for x. A gear that has 30 teeth, okay, and teeth would be t, so that would be 30 under the k, makes 25 revolutions a minute, so that's 25. Now this lets us set up for k. If I multiply both sides times 30, because that's clearing the denominator here, if I multiply both sides times 30, what I then get is 30 times 25, which is 750, equals k. Now it says how many revolutions per minute will a gear that has 50 teeth make? So my equation again is v equals 750 over t, and the second half of the sentence is clearly talking about 50 teeth, so my v is equal to 750 divided by 50, because t is the number of teeth. And you do your simplification, the v is equal to 15 revolutions per minute. So you can see that the more teeth you have, the fewer revolutions per minute, but it is easier to pedal. Alright, so now we have another problem here, and it looks like they have a square of the distance in this problem. Notice the word square. Okay, so the intensity of a light source is inversely proportional, so there's my inverse, to the square of the distance from its source. So the first sentence sets up the equation. Then the first half of the second sentence gives us our ability to solve for k. If the intensity, now this is, again, to describe this a little bit, the intensity of a light source is inversely proportional to the square of the distance from the source, which means that if you're further away from the flashlight, it's less intense. And that makes sense because, you know, if you're very close, the flashlight is very bright. Think of your cell phone flashlight. Very bright up close, but then further away, someone may see a little white dot, but, you know, there's not getting blinded by that cell phone flashlight. So this makes sense, and this is squared since we're dealing with a little bit of this physics here. So it says the intensity at 48 lumens at a distance of 12 feet. Okay, so this is giving us the information to solve for k right there. So if I go 48 over 48 is equal to k over 144, I would then multiply both sides by 144. Looks like I got an Adobe pop-up, so I might have a little glitch here. So 48 times 144 is going to be 6,912 for my letter K. I'm going to intensity is equal to 6,912 divided by d squared. And now I get to answer this question: what is the intensity of a distance of 6 feet? Well, the intensity is going to be our 6,912 divided by 36, which is 6 squared. So my intensity at that distance is going to be 192 lumens. 192 lumens at 6 feet. So you could see that at 12 feet, that flashlight was only 48, and at 6 feet, it's a lot more intense. Hey, good morning. All right, so let's move to the next problem. All right, so here we are. Frequency of vibration F in an open pipe organ varies inversely. Woohoo! Another inverse problem. So for our final problem today, we're dealing with inverse problems. So this is going to be y equals k over x, and it says that the frequency of vibration F in an open pipe organ varies inversely as the length L of the pipe. Now let's talk about the air of the pipe moves the air in the pipe 3 meters long, so that would be the length of the pipe, so we're going to go with k over 3, vibrates at 90 times per minute, and that's going to give me my letter k there. So if I multiply both sides by 3, I get k is equal to 270, which is great. Now I know my letter k. Now I'm going to put that into the new equation. The frequency is 270 over our L, and this actually brings about the concept that if you have a longer pipe, you're going to actually have a lower note. And people who are interested in subwoofers and maybe some of the technology that creates really, really low bass in very, very small spaces, generally those beautiful bass-sounding subwoofer systems have a cavern where the bass port is tuned to a low frequency, and that way you can get a very low bass out of a very small object. It's not just the speaker size, but it's also the size and the tuning of the speaker itself. So just dropping a speaker in a box is okay, but you should really know the measurements of that chamber that you're putting it into. All right, so now find the frequency of a pipe that's 2 meters long. So what we're doing is, instead of moving with a 3-meter pipe, we're moving with a 2-meter pipe. So what's going to happen is that the note should go up. So shorter, think of a flute or a piccolo, plays higher notes than a tuba or a saxophone. So if I put 2 here, the frequency should go up higher than 90, and so it will, because the frequency would be 270. 270 is the vibrations or times per minute right there. And thank you for watching today. I hope this video was helpful to you. I know I left the units out of most all of these problems, but I was able to grab them at the end of the problem from what they were used in the beginning. So thank you very much, and I appreciate you watching.